100 years ago, Einstein proposed a new theory of gravity called the general relativity theory. We live in a four-dimensional space-time universe, which means three space dimension and one time dimension. Three dimension means we can move from side to side, forward and backward, up and down. We do all this stuff in time dimension. Time goes forward into the future. Space-time in which we live is dynamic, which means it can be stretched, shrinked and curved in the presence of matter and energy. Einstein came up with general theory of relativity because no one couldn't explain why an object moves towards the ground. When he was in his office, he has what's called his happiest thought. He imagined a man falling from the roof. He said that man wouldn't feel gravity as he accelerated downward. Einstein imagined that if you are inside an elevator and accelerated upwards in outer space where there is no gravitational field, the person would still feel like there is gravity. If he took something out of his pocket and dropped it, it would fall on the ground at an accelerated rate, just as if he were standing on an ideal stationary elevator on the surface of the earth. So he realizes what he calls the principle of equivalence, that the effects of gravity and the effects of acceleration are equivalent. So there must be one explanation for gravity and acceleration, and that's what the general theory of relativity is. General theory of relativity describes the curvature of the space-time and the distribution of matter throughout space-time. Gravity is a result of curved space-time created by mass. This is Einstein's equation. G mu nu equals 8 pi by g by c to the power 4 times t mu nu. G mu nu is the Einstein tensor which is used to express the curvature in space-time. 8 pi g by c to the power 4 is the constant used in this equation. T mu nu is stress energy tensor used to determine how much mass and energy is there in space-time. So what does this equation tell us? It tells us that matter tells space-time to curve and space-time tells matter to move. Because space-time is curved, the object moving through space will follow the straightest path along the curve, which explains the motion of the planet. They follow a curved path around the sun because the sun bends space-time around it. Planets in the solar system follow the shortest path that requires the least amount of energy, and this results in the motion we observe. When there is no mass warping the space-time, light travels in a straight line and it looks like this. But when there is heavy mass on space-time fabric, it will bend light's path and it looks like this. This is called gravitational lensing. In 1919, an expedition was set out by Arthur Eddington to prove that light's path is bent when there is heavy mass on space-time fabric. He observed that light ray from the star behind the sun curved due to the curvature in space-time made by the sun. With this conclusion, warping of space-time was proved, and so was Einstein's general relativity. Over 100 years ago, after proposing general relativity, Einstein predicted the presence of gravitational waves which are caused by the attraction of two massive black holes on each other to form a bigger one. The waves produced is so hard to detect because the size of the effect of gravitational wave was 1,000th the diameter of a proton. What gravitational wave does is that when an object is placed in this way, the object gets compressed in a particular direction and gets elongated in another. This was the main idea for the LIGO team, which recently discovered gravitational waves. Using interferometer, a device that separates a beam of light into two ray beams, usually by means of reflection, and that brings the rays together to produce interference used to measure wavelength. The LIGO's interferometer has arms that are about 4 km long, and the laser produces the purest light. The two beams are split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out. But when a gravity wave comes along, it dissolves space and changes the distance between the mirrors. One arm becomes a little longer than the other, and an instant later they switch, due to which the alignment between the peaks and valleys of the two returning light waves no longer cancel each other out when added together in the combined beam. Now, some light does reach the detector with an intensity that varies the distance between the mirrors, and you are measuring gravity waves. Only because of Einstein's general theory of relativity, the LIGO team were able to prove the existence of gravitational waves. Thank you for watching.